sorry, I cannot pause the videos when I'm making them. So when I have to stop for the kids, then I have to kind of start a new video. I can't pause it and restart. So we were going over, right, you've already done your observations up here, right? You talked about all 5 of these characteristics, right, and what you saw. And then you come down here to make a conclusion about whether or not it's a metal, non-metal, or metalloid. And we talked about this in class and the time we did the activity, right? But you have to be able to observe all characteristics that make a metal a metal, right? Those are non-negotiable characteristics. If you see 3 out of the 5 or 4 out of the 5, you can't just assume that the other characteristic is just there and just say, well, it's 4 out of 5, so it's a metal, right? You're not a metal by definition unless you meet all of those, you have all those characteristics. So again, you're pretending that like your sample is like a new element, and based on what you know makes a metal, can you actually say for sure it's a metal? And you cannot say for sure unless you've been able to confirm all those characteristics. Same thing with a non-metal. The only exception to that could be if you had a gas, because then only a non-metal can be gas at room temperature, right? But that we've learned so far, right? So most of these you're going to be saying probably that you can eliminate one answer choice, we practiced that a lot in class, but we were talking about what if you had a sample that was solid and it was malleable, right? And you were unable to determine anything else on that sample. Your answer would be, well, okay, I know for a fact there's no way it's a non-metal because non-metals are not malleable, right? But until I could do further testing on its ductility and if it was lustrous or dull or if it was a conductor or not, right now you don't have enough information to determine whether it's a metal or a metalloid, right? So that's how you kind of want to do your answers, right? So if you can see all characteristics of a metal, then you can say it's a metal. If you can see characteristics of a non-metal, or at least see one characteristic that's unique to non-metals, then you can go that way. If not, then you're usually going to, like I say here, right, you're usually going to eliminate the wrong answer and state why you can't determine between the other two, right? So then there's going to be a station. The second station is going to be, there's going to be a test tube, probably up front on my lab bench that has a reaction in it and that has a hexane layer like we did in lab 3. And it's not going to be exactly like this where you would circle an answer choice like this. This was just kind of for practice to kind of refresh us on the information. But for this example, I told people in class, let's just pretend that you went up there and you saw a clear, or that yellowish clear, some people saw hexane layer when you went up there. So if you were to see this color here that corresponded to chlorine, because, right, you would have done some kind of control test, but you know what these colors are anyways, right? What possible combination here could have led to that hexane layer being that clear color that we see that would tell us that chlorine is in the hexane layer? And if you remember from lab 3, and you should kind of refresh these a little bit, that we had a potassium halide, right? So we had some halogen attached to potassium or bonded with potassium. We had a single halogen that was by itself at first, and we threw them in a reaction tube together, and we looked to see who the loser of that reaction was, right? You have 2 nonmetals that are technically competing to gain the one valence electron that potassium has to give off. So we were looking at the most reactive nonmetal in all those reactions, because the most reactive nonmetal was going to be the winner of that reaction, and it was going to go with potassium. And the loser was going to be all by itself, right? Not with potassium. And those colors that we see of those halogens and hexane, we can only see your color in hexane if you are by yourself, right? So if you're attached to potassium, we can't see you, right? If you're by yourself, we can see you. That's how we knew that the color of that hexane layer was associated with the losing halogen of the 2. So if we're saying that the chlorine layer was clear in this case, right, and we said that chlorine was on top, we had to find a combination here that could actually have chlorine being the loser. So if you look at your periodic table, right, out of the other choices here, right, we have iodine, bromine, and fluorine. Only fluorine is more reactive than chlorine. So obviously we had to have introduced fluorine with chlorine in that reaction in order for potassium to choose fluorine technically and kick chlorine off by itself. So you have to kind of remember that general way that those single displacement reactions work, I'll kind of write it up here. It was like AB plus C, right? And then you'd get AC plus B, assuming that C was more reactive than the thing it was competing with, which would be B. And again, in our case, right, we were looking at nonmetals, right? Halogens are nonmetals, and nonmetals gain electrons. So what was really happening is you kind of threw two halogens or two nonmetals in there, and then you have potassium that has one valence electron that it's able to give off, and they kind of go, you can think of it as like they're kind of in competition, right, to get that electron. And obviously the nonmetal that's more likely to gain an electron is going to be the one that gains it and therefore bonds with potassium, leaving the other one as the loser. So there'll be a place where you kind of want to generally describe like why you picked your answer choice. And what you'll have to do is, like, I think the way I have the question worded is like I think I have like a blank plus blank kind of thing where you have to write in like a halogen and a potassium halide that could have led to that particular color that you see up front. So like if this had been set up this way, right, you would have written like in a blank like F2 plus KCl. Another thing that could have led to this could have been technically KF and Cl2 as well, right? That could have also led to that clear layer, right? Because in this case, the F2 plus KCl, fluorine would have outcompeted chlorine, kicked it out. In this case here, potassium was already with the more reactive halogen, fluorine. So chlorine would have came in, tried to remove fluorine, but it would have been unsuccessful, right? So both of those would be acceptable answers, or would have been acceptable answers for full credit for this one. Then you'd want to kind of describe what was going on, right? What were the halogens doing? Why were they trying to get with potassium? Why is the loser on the hexane layer? And then you have to also describe or justify your answer with periodic trends as well. So in this case, if this were like the problem I had on my test, I obviously in this example would be looking at the reactivity difference between fluorine and chlorine. So I would actually write a justification explaining why fluorine is more reactive than chlorine. So I'd use all 6 of our trends, right? We'd have atomic size, we'd have shielding effect, Z effective, ionization energy, electronegativity, and electron affinity, right? So you have 6 different trends that you should be talking about to actually explain, well, why would this combination actually work, right? So proving why that nonmetal was more reactive, and then therefore, then how would that have led to that color in the hexane layer? Okay. This station, it'll be station 3. I have it set up in the practice test to kind of look like lab 2, where we had different metal chloride solutions, and we tested them with potassium salts to look for signs of a chemical change. In our lab 2, we mostly saw color change and the formation of a precipitate. In this example here, right, I kind of set it up like I had 5 different metal chloride solutions, and I lost the labels to all of them so that we had to do that potassium salt test and kind of rank it how many times they each reacted, right? So on the test that you guys take, you're not going to have the well tray with potassium salts and solutions. You'll actually will have like 4 different metals completely, and you'll be doing a test with another compound and looking for a different sign of a chemical change than just the formation of a precipitate, right? So make sure that you're reviewing the 7 signs of a chemical change that we could identify in a high school classroom, because the reaction that you're doing in class will not be the same kind as this, but the idea is the same, right? You're looking for who had more signs of a chemical change. Like when you go to test it, right? Who proved to be the most reactive out of all your tests? And then you'll go through and rank them. So in this like make-believe example, I said, okay, my unknown sample A, because again, like I lost all the labels to those metal chlorides, so I called them all A, B, C, D, and E. And then we did the test. A reacted no times, B reacted 3 times, C reacted once, E reacted once, and D reacted twice. So we can obviously tell from this that A is the least reactive, reacting 0 times, right? We can quickly look at this and see that B reacted 3 times, so that's the most reactive. C and D are both tied, right? They each reacted once. That maybe lets us know that they're probably equally reactive, and they're tied for second to last place. And then we have like rubidium here that reacted, right? It's the second most reactive one. So then you'll have something kind of like this. You're going to run 4 different metals through a test, and you're going to look for signs of a chemical change. And then you'll be able to rank, you know, unknown metals A, B, C, and D based on who was the most reactive to least reactive out of those choices after that test that you do. And then, just like what we did here, we would have to grab a periodic table. We'd grab a periodic table and look at, right, we can use our cheat to know what the answer was supposed to be, right? I can look at magnesium, nickel, ruthenium, rubidium, and cesium on the periodic table. And I remember that, right, if we're further from that stair step line, we know that you're more reactive. So we can use that cheat, right? We can take advantage of the resource that is the periodic table, right? It was built like that on purpose. So out of all these choices here, looking at the periodic table, you would see that cesium is the furthest from the stair step line. So you know that cesium has to be the most reactive metal out of all of these. So that's why I put cesium chloride as the identity of my most reactive metal here, right? We see that the least reactive one would have been nickel, right? So that's why I assigned it to A. The second most reactive one, right? If you look at the periodic table, right underneath cesium, or right above cesium, excuse me, you have rubidium. So then we know that, right? Cesium is more reactive because it's further down in that family. So then we can assign rubidium to 2, and also that stair step cheat still works, right? Cesium is technically 1 step further from the stairs than rubidium is. And then 1 reaction with C, 1 reaction with E. So those seem equally reactive. And when you look at the table, you see that manganese and ruthenium are both the same amount of steps from the staircase, right? So then the cheat tells us that they should be equally reactive. And then you actually see that they're equally reactive here on the test. But we don't have enough information to say who is who, right? So we know for a fact that ruthenium and manganese are C and E, but we don't know who's who, which is why my answer says it's manganese or ruthenium chloride. And this one is manganese or ruthenium chloride, right? I don't have enough information to say for sure who's who. So I have to kind of leave it as it's one or the other here. And then after you've kind of done that, then you'll have a justification, and I have like another page, another blank page attached to this to keep writing. But you'll have to go through and justify, right, why you assign them all like this, right? So if this were me taking a test, I'd have to go into talking about why cesium was the most reactive out of all of those, right? I'd be talking about why these two were equally reactive. I'd be talking about maybe why this one was the least reactive, so on and so forth. So there's a way to do it, right? Like where you can technically kind of end up talking about all what you'll have as 4, right? All kind of at the same time, because you'll see some that might be in the same period or in the same family and some in different ones. But you don't have to write like, you know, it's not like you have to do all 6 trends 4 different times. There's a way that one justification can kind of incorporate and kind of compare and contrast all the different metals that you have. So make sure that you're reviewing your justifications for metal reactivity, and that on this question here, you would have to do it for non-metal reactivity, right? And talking about the trends for non-metals and relating it back to that single displacement reaction. So say your trends, make sure that you are familiar and can remember all these characteristics here, because I don't give those to you. You have to know those, so on and so forth. But this test, the lab test here isn't too bad. People, I think the average last year on this one was like an 88%. So I'm pretty confident you guys will do fine. And then since I missed 2 days last week, I was originally going to schedule that the written test for Tuesday, but I want to spend Tuesday doing kind of one more day of like review and practice, and then schedule the written test part till after Thanksgiving. So we'll do review in class Tuesday, and I'll probably make another video going over more stuff on that section later. Probably post that like Monday night or Tuesday night. So that's all for now. If you missed it, I'll take a picture of this as well and upload it to our classroom in case you want to kind of see what I wrote if it's hard to see in the video.